Hey guys, today we are really going to dig into derivative rules, and so we're going to go about discovering at least the power rule, and then we're going to kind of work our way from there. Um, since we have a good understanding of limits, we can develop derivatives very quickly. Recall that we defined the derivative f prime of x of a function f at x to be the value of the limit, and there's actually two of them, right? So there is the limit of f of x plus h minus f of x all over h as h approaches 0. This is your standard form of the definition of the derivative, or the alternate form, which you don't see as often, but can pop up in especially multiple choice questions, so watch out for those ones. F of x minus f of a over x minus a, as x approaches a. Okay. So this is your standard form of the limit, and this is what we'll be using, standard form of your definition of the derivative, and we'll be using this one the most. So let's, for example, we're going to start looking at derivatives of different function families and what they have in common, and from there we'll start figuring out the rules, right? So the graph of a linear function, so let's say, for example, y equals 2x plus 3. This is a linear line, a straight line with a slope 2. Now, since the derivative is your slope of your tangent line, and this has a constant slope, then we would expect that the derivative should be our constant slope 2 at any point, right? So if I do a little sketch over here to kind of explain what I mean, right? If you have your graph, so 1, 2, 3, 4, 5, 6, 4, 5, 6. And when you try to graph this line, we start up 3, and then we go up 2 over 1, down 2 over 1, down 2 over 1, and so on and so forth, right? We get this linear function with a constant line slope. So if you picked any point, so if I picked any point on that line and I drew a tangent line there, right, my slope would be 2. And it doesn't matter where actually on there I draw it, but my tangent line would always be a slope of 2. So basically what I'm showing you is that if you take the derivative of this function, right, you should get, no matter what your x value you plug it in, you should get 2. So when I take this derivative of using this limit function, I should just get out 2 at the end. All right, so again, to use this, we define f of x is 2x plus 3, and then f of x plus h would then be 2 times x plus h plus 3. So I'm going to show you that we should get out our derivative, our slope of 2. And then this limit notation should follow all the way down. So limit as h approaches 0 of f of x plus h, so 2x plus h plus 3 minus parentheses, the 2x plus 3, all over h. Then we're going to go ahead and start simplifying the top. So distribute that 2, distribute that negative, and we get the limit as h approaches 0 of 2x plus 2h plus 3 minus 2x minus 3 all over h. Let's see, 2x and 2x cancels, plus 3 minus 3 cancels, and then my last term I have left is 2h over h, and so I can go ahead and I can cancel out those h's. And so then now, if I'm taking the limit as h approaches 0 of just the number 2, right, I definitely get out 2. And that was what I was expecting. So I should have my derivative of 2x plus 3 should just be the number 2. All right, let's also go ahead and look at a constant function. So we have actually shown that the constant function of f of x equals c would be 0. We expect this when we're looking at a graph of a constant function such as y equals 3, because if I asked you to find the slope of this graph at any point, right, the slope of the tangent line, you would get, no matter what, your slope would be 0. Cool? All right. So then let's go ahead and we'll look at some powers of x. So we are going to go ahead and directly compute the derivatives of a few powers of x, like x squared, x cubed, 1 over x, and then the square root of x. One thing to note is you might be looking at these guys and thinking, what the heck, those are not polynomials, right? They don't have an x squared and x cubed. But I want you to remember that technically I could rewrite these two functions, this rational and this radical, as powers of x, right? 1 over x would be the same thing as x to the negative first power. And so that technically is a power of x, and then the square root of x is technically x to the 1/2 power. Okay? All right, so we're gonna go ahead and let's first start with the derivative of x squared. So we're going to do the same thing that we did with our linear function, and we're just going to find the derivative of this using the limit definition. So our f of x is x squared, and f of x plus h then would be x plus h squared. All right, bring that limit notation with us the whole way. So the limit as h approaches 0 of f of x plus h, which is the x plus h squared, minus f of x, which is just x squared, all over h. Now, technically, off to the side, right, when I do this, I have to FOIL. So I'm going to do x plus h times x plus h off to the side. So I get x squared plus xh plus xh plus h squared. Okay, so then when I come back in here, wow, I have x squared plus 2xh, because I have 1, 2 of them, plus h squared minus my x squared from up here still, all over x, or excuse me, h. Then I see some things that can cancel, so my x squared cancels with my negative x squared. And then from what I'm left with, I have in my numerator, I have an h as a greatest common factor in both of those terms. So my h can come out, and I'll be left with 2x plus h all over h. So now my h's can cancel, the problem causers. And I would get the limit, oops, don't write over there yet. The limit as h approaches 0 of 2x plus h. So now if I go ahead and I plug 0 in for h, my limit, or my derivative, would be 2x. So thus the derivative of x squared is 2x. The slope of your tangent line would be 2x. The instantaneous rate of change would be 2x, and it would just depend on your x value. All right. Now we're going to go ahead and compute the derivative of x cubed, because we're just going to try to identify what the pattern is that's happening with our derivative rules. So f of x would be x cubed, and this is good practice too, arithmetic and algebra skills. Right, f of x would be x cubed, f of x plus h would be x plus h cubed. So now I'm going to go ahead and I'm going to find the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, this means I have to FOIL it out actually 3 times. So I'm going to come over here so I don't run into any room or run out of room. X plus h times x plus h times x plus h. So we'll FOIL the first two together. We'll get x squared plus xh plus xh plus h squared times x plus h still. And I can actually go ahead and in this middle combine those terms. There's 2xh there. All right, and then now I can go ahead and I can distributive property or FOIL out these ones as well. So I'm going to do my first term, then my second, then my third. Okay, so x squared times, x squared times x would give me x cubed. X squared times h would give me x squared h. All right, now with my, I don't think that yellow is going to be good. We'll change it to a gold color instead. 2xh times x would be 2x squared h. 2xh times h would be 2x h squared. And then last but not least, we got h squared times x, which would be h squared x, plus h squared times h would be h cubed. Wow, okay, so then we have a lot of stuff going on. So I have the limit as h approaches 0 of any combined terms. So I got x cubed, x squared h, and a 2x squared h would give me 3x squared h. Okay, then I have 2xh squared plus 1. Oh, this should technically can xh squared, right? I could rewrite this with the x in front, so then it matches more nicely with this piece right here. So if I have 3 of those, 3xh squareds, and then 1h cubed at the end, and then I still have from up above previously my minus x cubed right there. Oof, and then that's all over h. Like I said, good practice with arithmetic and algebra and foiling and all that fun stuff. All right, stuff that cancels. My x cubed and my x cubed go away. So then I have a GCF of an h in my numerator, which is good, because once I pull that h out of these 3 terms, I'll be left with 3x squared plus 3xh plus h squared, all over h still. So then those cancel out. So then really I'm finding the limit as h approaches 0 of 3x squared plus 3xh plus h squared. And when I plug in h, or when I plug in h approaching 0 to find the limit, this goes to 0. Oops. This goes to 0, and this goes to 0. So then my final answer would just be 3x squared. Thus, the derivative of x cubed is 3x squared. All right, so last but not least, here is a summary of the computations we have done so far. So with our first linear function, we had 2x plus 3 was our function, and we found that the derivative was 2. For our x squared function, we found that the derivative was 2x. And then for our x cubed function, we found that the derivative was 3x squared. So go ahead and take a look at these, and between now and the next video, see if you can figure out what the pattern is. See if, without having to calculate your limit definition every time, you can figure out the shortcut that gets you from your function to your derivative. Then we'll pick up the power rule in its full glory in the next video.